by Markus Tempelmayr, a diagram-free approach to the stochastic estimates and regularity structures. Please.
Yeah, thank you very much for the introduction and for the possibility to speak here. So what I want to talk today is joint work with Pablo Linares, Felix Otto, and Pavlos Tsatsoulis. And it's on stochastic PDEs, more precisely on regularity structures and more precisely on how you obtain stochastic estimates in this business. That's what Hendrik called in his first lecture, I think, bounding the trees. And we will try to do that completely without using trees. So so of course that's maybe not your topic. So if you get completely lost, please let me know so I can do it slower. So we consider the following quasi-linear equation where you have on the left-hand side a heat operator. So you think of 2 as the time direction and 1 as the space direction. And on the right-hand side, a non-linearity, A, that you can assume as being as smooth as you want. And a random rough driver xi, where at the moment it's not so important what exactly that is. You just think of something that's very, very rough, even a distribution. And then this equation is what's called a singular SPDE. And I want to remind you what it means for an equation to be singular. So if you assume for a moment that xi has Hölder regularity alpha minus 2, then the best we could hope for is that the solution u, if we can obtain somehow a solution, will have regularity alpha. Even a solution to the linear equation would be just by 2 better than the right-hand side. But then also, since A is smooth, A of u is in C alpha, and the second derivative of u is back in C alpha minus 2. And then you have the problem that in the product of A of u with the second derivative, this product is only well defined if the sum of the 2 exponents, alpha and alpha minus 2, adds up to something positive. And that means that alpha has to be larger than 1. So if alpha is less than 1, then somehow there is a problem in this equation, and it's not clear what does it mean to be a solution. On the other hand, the equation is what's called subcritical as long as alpha is positive, and that just means if you zoom into the equation and look on very small scales, then basically the non-linearity drops out and you just see the linear equation. And that means somehow you can expect that on small scales, your solution will look like the solution to the linear problem, and that gives you hope to do at least something. So why should we care about that? Okay, so something that people typically like to do is taking space-time white noise for the driver xi, and that would correspond in one space dimension, as I wrote the equation here, to alpha being 1/2, and that's already far away from 1, so there is already a problem. And if you go to dimension 2 and take space-time white noise, then that would already correspond to alpha being 0, and the equation is not even subcritical anymore. Now, what's the goal? What we want to do is to provide a solution theory for this equation in the full subcritical regime, so just for positive alpha. Now, how do you do that? So for that, the theory of regularity structures by Martin Heira was invented a couple of years ago, where the basic idea is so the theory comes in 3 big steps. You do first an algebraic step where you build somehow some local, so the idea is to approximate your solution by local expansions. And in this first algebraic step, you look for these building blocks for your local expansion. So if everything were smooth, you would do a Taylor approximation, and the building blocks would be the monomials. So now we are in a rough setting, so we have to add something to the monomials, more general objects. Then in the second probabilistic step, what you do is to estimate in stochastic norms these building blocks, these local expansions that you came up with, and they should be completely uniform in any smoothness of the noise, so you can obtain some limiting object. And then once you have these estimates, you can use them to run an analytical step, namely a deterministic solution theory, to actually obtain a solution. And what I want to speak today is mainly the second point. So how do you get these stochastic estimates? But of course, I also have to tell you what are the objects that we want to estimate. And for all who know regularity structures, that's the analogon of the Chandra-Haira paper. Okay, so now more precisely, what's the assumptions on the noise psi? So first of all, we assume that it's qualitatively smooth. That means we can write down the equation and we will get a solution. And we think of this as being an approximation to the actual Roth object that we are interested in. And the problem is, if you give this regularization on the noise away, then your family of solutions won't converge to something reasonable. So that's the problem. We also assume that psi is stationary and reflection invariant, but that's more to make things simpler later. And the crucial assumption is the last one, namely that it satisfies a spectral gap inequality. That means that for all sufficiently smooth functions f, where everything I write down makes sense, we require this infinite dimensional Poincaré type inequality, where on the right hand side this is just think of the Fréchet derivative of a function f with respect to the noise in some so h star is some Sobolev space, and in our case a very specific one, but not so important. Now which random variables would satisfy that? For example, Gaussians with Cameron-Martin space H would satisfy A1, 2, and 3. And if you then also modify it with a smooth kernel that preserves some symmetries, then it also satisfies in addition A0. So if you want, you just think of white noise if that helps you. Okay.
Do you also need to assume that the noise is smooth in time?
Yes. Space-time, sorry. I'm in a space-time setting, so yes. Now, as we saw already yesterday in Hendrik's talk, so the equation has to be modified to get some solution. And we just do a very pragmatic ansatz and say, okay, let's subtract something, h of u, where a priori it's allowed to depend on the non-linearity A, on the solution u, and on the driver psi, and also on the space-time point y. And of course, that's somehow a meaningless counter term, because now I could take h to be equal to psi and all my problems would be gone. But of course, that's not in the spirit of renormalization. So we have to postulate something on the counter term that also a physicist somehow would be happy with. And what we do is we assume it's local in the solution u. So it depends on u only through the space-time point y. We assume it's shift invariant in space and time. And by the stationarity of the noise, that's actually already equivalent to being deterministic. So that just means we drop the explicit dependence on psi. It only depends on psi via its law, but not on the realization. And we also drop the explicit dependence on y. So we end up with this here. And then comes the most subtle postulate, which says that we want it to be shift covariant in U space. And that means if I have a counter term for a nonlinearity A and I shift the solution U by a constant, then I want it to be the same as the counter term given to a different equation, namely where I replace the nonlinearity by a shifted nonlinearity, but with the original solution. And that's a very complicated way of saying the origin in U space has no effect on renormalization. So whether we measure, think of U as measuring temperature, whether we measure in Celsius or in Kelvin shouldn't have any effect on renormalization. Okay, and that translates into this complicated counter term. So it's a function of the nonlinearity, and the nonlinearity gets shifted by the solution itself. Now we have a modified equation. And now is the point where we try to get these local approximations to this equation. And the philosophy to do that is that we do not consider one fixed equation, but we consider all nonlinearities A at once, and also the whole solution manifold. Since it's a PDE, the solution manifold is infinite dimensional, and therefore we think of it as being parameterized by space-time polynomials P. And that way we can somehow see the solution U not only as a function of space and time, but also as a function of the nonlinearity and this parametrization. And therefore we can take derivatives with respect to the nonlinearity and the parametrization. And we do that by assuming the nonlinearity is smooth. So you have Taylor coefficients, and then you just take derivatives of your solution with respect to these coefficients and evaluate in the end at A equals 0 and P equals 0. And this object I denote by pi beta. So beta is a multi-index and tells me how many derivatives in how many directions do you take. And the same we do for the counter term. So also the counter term is a function of the nonlinearity, and we take derivatives with respect to it. Now, what do we gain by doing that? So the idea is that the equation for U, so remember U satisfies an equation, that translates now to an equation for all these pi betas. And what you get is an infinite list of equations. For every beta, you get an equation. And the nice thing is that these equations are linear. So we have linearized our problem, namely for the simplest multi-index 0, meaning no derivation at all. We just see the linear stochastic heat equation. For the next multi-index, say E1, that means I take one derivative in direction of A1. We get the equation where on the right-hand side, we see pi 0, second derivative pi 0, which we already have solved, minus a constant. And this constant is coming from the counter term, and that we still have to choose. And you also see that since we made this complicated ansatz for the counter term, that translates on this level on this to this complicated expression. So we do not just always subtract the constants CE1, CE2, C2E1, but also something that looks a little bit more complicated. But actually, that's something very, very useful. So the message is, so far we turned our nonlinear PDE into an infinite hierarchy of linear PDEs. And now these objects are almost these building blocks that we want to work with. The only thing we have to do is we have to include also polynomials, since it should somehow be a generalization of a Taylor. Think of a Taylor expansion. We want to have polynomials inside. And we just do that by postulating pi x on a multi-index En. That means take one derivative in direction Pn. Is the monomial centered at x to the power n. And for all the other multi-indices beta, we postulate the same equation as before. So here the pi beta minus just means this complicated list that you saw on the previous slide. And to make it a unique object, you also need some boundary condition, and you take your favorite boundary condition, whether you're on the torus or on the whole space or wherever. And what you also want is that these expansions vanish at the center x to a specific order. So to every multi-index, you have this what's called homogeneity, and you want your guys to vanish to the right order, just as monomials do. And that has the problem that now you asked for too much, a boundary condition, and this vanishing is too much. So what we do is we want to satisfy the PDE only modulo polynomials of a certain degree, but I think you can just ignore that for the sake of this talk. And what's also required in this business of regularity structures is a linear transformation that takes an expansion around one point and spits out an expansion around another point. And that's called a structure group. So the structure group should contain these elements. I call it gamma xy, that just transform linearly one expansion into another. Okay. Now we have everything together to finally formulate the main result. And it says that assuming that xi satisfies our assumptions, then for every space-time point, x and y, all the objects I wrote down somehow make sense, exist, and we have these stochastic estimates. We can estimate these stochastic norms. And that's exactly the estimates you want to run in the end a deterministic solution theory. So that's really the main difficulty in this business. Okay, so how do you obtain these estimates? So the idea is to use so remember, I will show you how we obtain this estimate for pi. And what you do is you apply spectral gap, not to pi, but to pi minus, to pi x beta minus, which was the right-hand side of our linear PDE. And that translates into, after some work, so not only for the square, but also for arbitrary p, you get this inequality. And what's good about this, so what we want to estimate is this object, or I mean almost without the minus, but first step is estimated with the minus. The good thing is now you estimate this norm in terms of the expectation and in terms of the derivative. And why is that better than just estimating the norm itself? Because the expectation we can somehow control, because in this pi x beta minus, that's the right-hand side of the equation, there were these red constants flying around, we can still choose them. And now we will choose the constants exactly such that we can control the expectation. And that's what's usually called BPHZ, renormalization. And why is it better to estimate that the Maillard or the derivative of the right-hand side? Because the derivative in this case is something good. It makes you more regular, because taking a derivative with respect to the noise basically means you throw away a noise, and throwing away a noise is something good because that's what causing the problem. How we exactly do use that is by duality. So instead of estimating the Fréchet derivative, you estimate the directional derivative in direction of an element delta xi in the Cameron-Martin space of your noise. That has the advantage that so when you take this directional derivative, basically you replace a noise xi which lives in C alpha minus 2 by an element delta xi which is in H alpha minus 1/2. So you gain 3/2 derivatives on the wrong scale, but still you gain something. And that's exactly what allows you to find a map d gamma, just some linear map d gamma, such that this increment vanishes to a higher order, namely to some order plus 3/2. If you wouldn't do the Maillard derivative, you would never be able to find some map that does that, and you would only get the alpha, and that's bad. Why is that good that we have it? Because we have this crucial identity that relates an increment of delta pi minus with an increment of delta pi. So two things are important here. Here is a beta, and here are beta prime and beta double prime, and they you can think of as smaller. So they came in our list of equations before. And that allows us to perform an induction, namely to estimate something on level beta. We just need to know estimates on smaller multi-indices beta prime and beta double prime. And in addition, in this increment, we gained 3/2, which makes this product somehow not singular anymore. So you can estimate this product. And now we are somehow far away from estimating pi. So how do you go back to pi? So the idea, now we have this increment of pi minus for a multi-index beta. And by some brutal, say, triangle inequality, you can bound also delta pi minus for this same multi-index beta. Then the spectral gap inequality allows you to go to pi minus for the same beta. And then you just do some simple Schauder estimate to go from the right-hand side of the equation to the solution of the equation. And now you have estimated pi on level beta. That's exactly what we wanted. But at the same time, it's already the input for the next level. So now you can go to a higher multi-index and use these two estimates again to run the induction and go up, 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 up. Okay, so let me summarize. What we do is that we approach the counter term rather top down than bottom up. So that's different than what's usually done in the theory usually, and maybe we see that today, what Hendrik is doing. You do first your local expansions to your equation. You get some, in his case, trees, and then you see, okay, I cannot estimate these trees, so you modify them. And then you have to look for how does this modifying the trees actually translate to the level of the equation. So what's your modified equation? And we don't have that problem, so we don't have to figure it out because we started by modifying the equation and then did the local expansions. And that has the advantage that we can build in symmetries from the very beginning. So we do not have to work hard in the end to say now our modified equation still has some symmetries. And what I personally like is that we get rid of combinatorics and algebra and replace it by more analysis, namely by taking derivatives with respect to the non-linearity and the noise, instead of having these Feynman diagrams. And yeah, let me also say again, the spectral gap inequality somehow complements very well the usual philosophy of BPHZ renormalization, because in BPHZ you try to make the expectation vanish, and spectral gap exactly estimates what you want to estimate up to the expectation which you now have under control, and the derivative, which is better because you have less noises. Okay, thank you very much.
Thank you very much. Would there be any questions?
When you do this renormalization stuff, usually there are what the people call the renormalization group freedom. No, so the constants you can choose them up to something. No.
Yes.
And so how this renormalization group transformations reflect into your approach?
So in our very concrete example, so I didn't say it, but we consider this equation on the whole space. And because we are on the whole space and we want this estimate also to hold for every x and y on the whole space, actually there is no freedom. So the constants we chose turn out to be exactly the constants you have to choose. If you would go to the torus, for example, there would be some freedom, but we haven't done that yet. And we also don't know how the renormalization group looks like in our setting. So in this precise setting, there is no freedom, but in principle, there would be, yes.
Thank you, Markus, for a very nice talk.
Thank you very much.
Thank you again.